Hello, welcome to the presentation Infrastructure for Healthcare Systems. In this presentation, we will discuss about the different types of infrastructure healthcare systems can run on. The infrastructure evolution is strongly tied to the architecture of the applications running on it. This is the reason why we will also briefly discuss about the evolution software architectures have experienced over the years. The author of the presentation is Javier Esparza, and this is a virtual avatar, automatically generated for guiding you throughout this presentation contents. In the next slides, we will begin introducing the different layers a typical computer system can be broken into. Regarding the infrastructure layer, we will discuss about the two main infrastructure types we can select today, either on-premise infrastructure or cloud computing. Then we will review the most important concepts revolving around cloud computing. Next, we will present the concept of edge and fog computing. Finally, we will briefly review the evolution of software architectures. Before and foremost, let's review how a regular computing system is internally organized. As we can see in the picture, we usually identify three main layers: the infrastructure layer, the systems layer, and the applications layer. The applications layer includes all the end-user applications. These applications provide functionalities or capabilities to the end users. To that end, they have a specific architecture, which internally organizes components and connections to realize the required functionalities. Later on, we will briefly analyze the most common types of architectures found today. Applications make use of libraries and run on top of different frameworks, environments, or platforms. All these elements reside in the systems layer, which also includes the operating systems. In short, this layer provides all the basic support required by higher-level applications. Finally, all systems and applications must run on a specific infrastructure. The infrastructure layer includes hardware, devices, and networks, and we can identify either on-premise infrastructure and cloud computing. We will talk about these two types of infrastructure in the next slides. We will first talk about on-premise infrastructures. With this type, all the computing infrastructure is owned by a company which installs, operates, and maintains all physical systems. Two main approaches have traditionally been followed, either using mainframes or clusters of machines. A mainframe is a very powerful server which runs both the system and the applications. It is a high-performance computer which contains a large amount of memory and multiple processors. It usually includes several replication mechanisms, exhibiting fault-tolerant characteristics. Some mainframes even allow hot swapping of some components. We are talking about very expensive machines, which are difficult to install, configure, and maintain. A different approach is to configure a cluster. It is a collection of inexpensive commodity machines. These machines typically reside in the same computer network and can easily connect with each other. All the machines work together and provide a view of a single system. To that end, the cluster usually runs some sort of resource allocator software system, which manages all the resources automatically. It distributes the different pieces of an application to different machines. To make adequate decisions, the resource allocator typically analyzes the resource requirements of the application and the current load of the available resources. It then plans for an optimal assignment. If a machine fails in a cluster, it is automatically detected and removed from the active machines. Machines may be easily added and removed as required. Maintaining an on-premise infrastructure is not an easy task. A different approach involves renting the infrastructure. This is the purpose of cloud computing, a computational model where the user consumes computation resources as a public utility. So computational resources like CPU, memory, or network bandwidth are consumed like water or electricity. In this model, the resources are not owned by the user. Instead, they reside in large data centers operated by specialized companies. The user requests the resources on demand, and they are almost instantly provided. The user has the illusion of having unlimited resources at her disposal, but she only pays by the consumed resources. This approach is also known as pay-as-you-go, and contributes to implement the concept of utility computing, that is, computing as a utility. Using cloud computing involves a number of benefits, but it is not exempt from some risks, which need to be highlighted. One of the main benefits involves capacity planning. Capacity planning means predicting the resources required by a system along the time. If the allocated resources exceed the demand, then the system is not efficient. If they are less than the demand, then the system becomes saturated. This is a very tough problem, sometimes impossible to solve. With cloud computing, the consumer does not need to make capacity planning anymore. Instead, the environment constantly monitors the demand, and it is able to inject new resources as required. Maintaining an on-premise infrastructure is very expensive. In addition to the cost of acquiring the equipment, important maintenance costs must be considered, like the cost of maintaining a specialized staff, electricity and cooling, security, etc. If cloud computing infrastructure is used, then the company must just pay a fee, without initial investments. Also, the provider shares its infrastructure among multiple consumers and benefits from economies of scale, resulting in cost savings for the consumer. With an on-premise infrastructure, the IT department becomes a very heavy burden for the company. Any change in the infrastructure is a very risky activity which typically involves prohibitive costs and long delay times. With cloud computing, any infrastructure evolution may be immediately applied, without upfront investments and with minimal risk. This typically involves organizational agility in a very competitive context where the fast company is the winner. With cloud computing, horizontal scaling is a simple task. The consumer requests resources and obtains them almost instantly. Similarly, resources can be released when they are no longer needed. This results in increased scalability. Finally, a cloud environment minimizes the recovery time using techniques like components replication, geographical distribution of components, or load balancing. All these measures result in increased reliability over on-premise solutions. Nonetheless, cloud computing also involves some risks. The first one has to do with security. As systems and data are moved to the provider, now the implanted security mechanisms are shared by the consumer and the provider. If these mechanisms are not compatible, some problems may arise. Also, the consumer loses control on the security mechanisms implemented in the data center. For example, the encryption applied to the data. Finally, as the infrastructure is shared by all the consumers, an attack experienced by a consumer may affect the remaining consumers using the same infrastructure. On the other hand, as the consumer loses all the control on the infrastructure, it is difficult to predict the performance of the system under specific scenarios, since it highly depends on the strategies implemented by the provider, which are unknown by the consumer. Another risk has to do with portability. Today, very few standards can be found in the different cloud computing platforms. This means an application deployed to a particular provider can hardly be deployed to a different provider without changes. This phenomenon is known as platform lock-in and prevents a consumer from moving freely between different providers. The last risk to consider has to do with legal matters. As data may be stored or processed in different countries, the data privacy laws applied at the provider might be different from the data privacy laws required at the consumer. As we have already seen, cloud computing platforms offer computational resources. Depending on the abstraction level of the offered resources, we can induce a simple classification. A cloud environment behaves as an infrastructure as a service or IaaS platform if the consumer receives low-level resources. By low-level resources, we mean CPU, memory, disk, or bandwidth network. To that end, the provider usually publishes virtualized resources the consumer can easily manage. In a platform as a service or PaaS environment, the consumer is able to deploy applications to the provider platform. In this case, the consumer does not need to manage virtualized resources. Instead, the consumer has access to certain tools which simplify the process of developing and executing applications. Finally, a software as a service or SaaS platform publishes a collection of functionalities which are directly accessed by the consumers. The consumers do not need to develop or deploy applications, they are already accessible, and the consumer just pays for the consumed services. Each service model assumes certain responsibilities and delegates the rest to the consumer, so each service model is appropriate for a different user profile. Let's consider a common technology stack for deploying any computer-based solution. This stack may include a collection of layers: the network, the storage, the servers, the virtualization, the operating system, the middle layer, the runtime, the data, and the applications. Within this framework, an infrastructure as a service solution publishes tools for working with virtualized resources, so it is in charge of managing networks, storage, servers, and virtualization. Then the customer is responsible for installing and configuring all the upper layers, which include operating systems, middle layers, runtimes, data, and applications. Thus, it is appropriate for system administrators. A platform as a service solution takes on more responsibilities, up to the runtime layer, leaving for the consumer just the tasks of managing data and applications. These tools are obviously more suitable for developers who build applications. Finally, software as a service solutions are final applications available for end users. Therefore, the consumer does not have any responsibility, she just makes use of the available functionalities. Deployment models help to classify cloud platforms according to the location and distribution of their components. We identify public clouds, private clouds, hybrid clouds, and community clouds. In a public cloud, the infrastructure is owned by a company. It is available to the public in general, so everybody may access it. Some examples are Amazon, Azure, or Google Cloud. In a private cloud, the infrastructure is also owned by a company, but it is available only to the members of the company. A hybrid cloud combines multiple cloud types. However, it struggles to publish an homogeneous interface to its consumers. Finally, a community cloud is an heterogeneous creature, where the infrastructure is shared by several organizations which pursue a common goal. In cloud computing, all data gets transferred to the cloud and all processing takes place there. If the volume of the data to transfer is very high, latency becomes too high and the solution is not appropriate for applications requiring fast reaction times, like real-time software or the Internet of the Things. A possible solution may involve moving computation closer to the data sources. Edge and fog computing represent this idea. In the case of edge computing, an intermediate layer between the data sources and the cloud infrastructure is imposed. This layer is typically a router or gateway which receives all the data coming from a local network and does some partial processing locally before transferring the results to the cloud. Fog computing involves yet another intermediate layer between the edge and the cloud. It aggregates multiple edge computing topologies. These solutions are specially tailored for the Internet of the Things networks. So far, we have been talking about the infrastructure. Together with the infrastructure, the software architecture has also undergone a great evolution over time, from monoliths to highly fragmented units called microservices. Software architecture refers to the structure of software, that is, how the software breaks down into components and connections between them. A traditional approach in software architecture involves adding all the functionalities to a single executable called monolith. With this architecture, when the software becomes more and more complex, it is more and more difficult to maintain. Also, scaling the system is difficult since it is scaled as a whole, even if some subcomponents require more or less resources than others. Finally, the reliability of the system is questionable. If some part of the monolith fails, it typically crashes the full system. The service-oriented architectures, or SOA, try to alleviate these problems. To that end, the monolith is broken into different reusable units called services. Each service is coarse-grained, and it implements a subset of the whole system's capabilities. Each service communicates with the rest through well-defined interfaces. This approach improves maintainability, since the code to maintain is smaller and presumably more cohesive. It also improves scalability, since each individual service may receive the resources it requires. And it improves reliability, since a service failure does not involve a full system crash. However, service-oriented architectures have presented some problems over time. On the one hand, coarse-grained services tend to get bigger and bigger, becoming new monoliths. On the other hand, in order to simplify services interconnections, a new component called Enterprise Service Bus is usually introduced. In practice, the Enterprise Service Bus becomes an extremely complex creature, difficult to configure, difficult to change, single point of failure of the whole system, removing many of the benefits we have commented so far. With these lessons learned, a renewed architecture based on small and autonomous services appears. We refer to microservice-based architectures. This architecture is specifically tailored for cloud computing technologies. Microservices are services with three main properties. They are small, autonomous, and they work together. Regarding its size, a microservice should implement a single capability, resulting in highly cohesive code. This improves maintainability and enables the release of new versions in very short development cycles. A microservice should be fully autonomous and have the capability to make decisions in an independent way. To that end, the microservice should be self-contained and include all the resources it needs. This means acquiring as few external dependencies as possible, resulting in low coupling and high reusability. In fact, to avoid dependencies, it is very common for microservices to include their own private storage instead of relying on external databases. Microservices work together, communicating with each other. In service-oriented architectures, it is common to see a service controlling the interaction with other services. This interaction pattern is known as orchestration. In the microservices world, there is no controller microservice, and all of them collaborate together in order to implement all the functionalities. This interaction pattern receives the name of choreography. Furthermore, communications in microservice-based architectures are usually asynchronous. This means events are triggered as they occur, and microservices are able to serve multiple requests without blocking periods. In a microservices-based application, many replicated microservices are concurrently running and communicating with each other. They are started and stopped dynamically as required. Also, failures must be automatically detected, and the crashed instances must be replaced by new ones. All these management must be automated by specific platforms. Today, the most feasible way to deal with microservices is to use cloud container-based technologies like Kubernetes. Thank you for your attention.